Hi class, welcome back to Electromagnetics. We'll wrap up our review session this time by reviewing the basics of the magnetic field. First, we want to do our historical background, again looking at different individuals who've contributed to electromagnetics throughout the years. So today we'll start off with looking at education of this person. I went to College Mazarin, I guess how you pronounce that, in Paris. And then College des Nations. Again, I don't know how to pronounce these. What did he do for work? He worked as an engineer in the French military. Here's an image of this person, if you'd like to try to guess. If not, you can probably guess who it is, who we've already talked about. It's Coulomb. Again, 1700s into the very early 1800s. Some notable things here are I did a major work called The Theory of Simple Machines. He was first to do major work characterizing electrical and magnetic forces, which led to the famous Coulomb's law, which characterizes the force between two electrical charges, which we've already explored some of that. And finally, as we've seen as well, the unit of electric charge was named after him because of all the work he did in this field. So again, we're still in part one, but this will be the last lecture in part one, which is review. So we've reviewed everything else up to now on the screen, and now we'll do magnetic field, and then after that we will get into the meat of the course. So just as before, experiments conducted at this time by a gentleman named Ampere showed that the following principles hold true for two charged bodies that are very small in size compared to their separation. Again, we've defined this before as point charges. The first is that the magnitude of force, and this is magnetic force, is proportional to the product of the currents and the lengths of the currents. So before it was proportional to the charge and the amount of charge, but this time it's proportional to the moving charge and the lengths that they're moving. The magnitude of this magnetic force is inversely proportional to the square of the distance between the moving charges. So this is just as like before. Again, it depends on the medium, just as the electrical field did. And then finally, the direction is a cross product of source and then the element acted upon. So I think we dealt more with dot products with the electric field, and we'll be utilizing the cross product while we're looking at the magnetic field. So just to touch base on some of the units we'll be dealing with, first is the Weber, and this is a Newton meter per ampere. Then the next is the Tesla, which is Weber squared per meter. Then we've got the permeability of free space. We talked about permittivity last time, which affects the electric field. Permeability affects the magnetic field. And this is denoted by mu naught. And the value for free space is 4 pi times 10 to the minus 7 Newton ampere squared. And again, this proportionality constant is what's utilized in item 1 from the previous page, which is mu naught over 4 pi. So just as before, the magnetic field is also analogous to gravitational field, with the exception that instead of a force associated with mass, the magnetic field deals with the force associated with moving charged bodies. Electric field was just with charge, but magnetic field, you have to have a moving charge to have a magnetic field. So let's look at this. Let's start to define some things. We're going to consider two current carrying loops, and they're going to be separated by a distance r in free space. And here's a diagram illustrating that. So you can see we have these loops, and they're broken up into these smaller distances which are DL1 and DL2. They both have a current in them of I1 and I2. And then we have this distance of R, and then these directional vectors, which would be perpendicular to the motion, the direction of motion. So DL1 and DL2 experience forces from the other pieces of the loop, which are designated as DF1, which that's the force from DL, the length 2, and then DF2, which is from the unit length DL1. So the magnetic forces experienced in this case can be generally mathematically expressed as follows. So we've got this differential force, force 1, which is going to be equal to the current I1 cross product with Ki2 DL2 crossed with A21 R2. So this is a little more involved than the electric field. Again, we've got these cross products we have to deal with for magnetic field. So we can also write the similar equation for DF2 the same way, just replacing the subscripts of 1 and 2. Since each current carrying element has an apparent field associated with it, the cumulative effect is a total magnetic field that is expressed in terms of magnetic flux density, and this is denoted by the bold-faced capital B. So again, when you see B moving forward, bold uppercase B, you need to think magnetic flux density. And so we can define this below for loop 1 and loop 2 as follows. So the magnetic flux density associated with loop 1 would be mu naught over 4 pi, the current times this differential length crossed with the direction over r squared, and likewise the magnetic field associated with 2, same thing with changing the subscripts. So with this new definition of magnetic flux density, we can now revise our mathematical description of the force acting on these differential lengths respectively as follows. So our differential force 2 is going to be equal to I2 dL2 crossed with B1, the magnetic flux density, and again dF1, the same thing, just reversing the subscripts. So we can now generalize these relationships in terms of the graphical definitions here. So if we have a current traveling along this line through this surface area, and we're looking at this point here, we have this magnetic flux density going in this direction, and then it'll be affected by this direction unit vector here and this angle for this distance r, if they're not totally in line with each other. So the equation falls out to this here. So this angle and this direction vector kind of take care of themselves with the cross product. So as long as we get these vectors set up properly, this should all fall out as it should. And so that being the case, we can now rewrite this equation for the differential force as I dl crossed with B. So we've got our I dl going this direction, and then we've got our magnetic flux density this direction. So if we cross those, that should give us our result. So we can now relate the force due to the magnetic fields back to the previous concept of moving charge as follows. So this differential force then is equal to the change of charge over time times this velocity times the change in time crossed with B, or this will be dqv cross B. So if we integrate both sides now, since we have differential components on both sides, we get that the force is now equal to the charge times the velocity, which remember that's a vector, it has a direction for this velocity, the product of those two crossed with the magnetic flux density. This now allows us to define the magnetic flux density in terms of the moving test charge in relation to the point in this following illustration. So if we've got this magnetic flux density, which is these lines sweeping across here, and we have this test charge that's in the presence of that field, we can find the instance of the magnetic flux density on that charge due to this total field, and we can see the velocity, so the charge is moving this direction. So if that's the case and we take the cross product, then the force exerted on the charge is going to be in the upward direction. Remember, we have to do the right hand rule and do the cross product, and that gives us a new vector that's perpendicular to both the other vectors. So in this case, the magnetic flux density will be equal to the force crossed with the direction over QV. And if we wanted to do as we did with the electric field, we can take this limit as we let that test charge go to 0. So now we can combine this equation for magnetic force with our previous equation for electric force. So both of those involve charge. Just one of them is the force exerted by just the stationary charge, and then the other one is the force exerted when the charge is moving. And so this was when we do this is called the Lorentz Force equation, and it looks like this. So the force is equal to the charge times the electric field plus the charge times the velocity crossed with the magnetic field flux density. And so we can simplify this, just say that Q times the electric field plus the velocity, vector velocity, crossed with the magnetic field. So this is the total force acting on a test charge Q moving with a velocity of v in a region with both an electric and magnetic field. So let's look at a quick example. So the forces experienced by a test charge Q for 3 different velocities at a point in a region characterized by electric and magnetic fields are given by these 3 equations. So the first force that we have is this. So you can see there's X component and a Y component. And so the X component only has the E field. The Y component, or Y direction, has both the E and has both an electric and magnetic component to that. Whereas on the second force, the X direction has electric and magnetic components, but the Y only has electric. And then finally, the third one, there's only electric field. And so this is the difference in these is, for the first one, you have velocity that's only in the X direction. For the second one, you have velocity that's only in the Y direction. And then the third one, you have a velocity, same velocity in the Z direction. Okay, so in this case, the V, E naught, and B naught are constants. And so we need to find the electric and magnetic field at the point. So again, copying this, the given scenario here. So from the Lorentz Force equation, which we just looked at, we're going to have that QE plus QVAX crossed with B is going to be, so this is the general form, and they only have the AX here because they're only moving in the AX direction, right? So this VOAX is what we put in for the V vector crossed with B, and so this will be equal to this part here as we move it down. So it's this QE naught AX EOV B naught AY, and so we can do the same thing for the next one. So this one, the only change is, remember, this is for the velocity in the Y direction. So again, we copy this equation down and put it equal to that. And finally, the third one, only in the Z direction, it'll be equal to this. That should be the resulting force. So now we can subtract the first equation from the second equation, and then the second from the third. When we do that, and again, this is just multiple unknowns, multiple equations, simple algebra, we come up with AY minus AX crossed with B is going to equal to B naught AX AY. So these two directions, this component directions crossed with the magnetic field is going to equal to this new value here. So when we do that, we can simplify this to that. Oh, that's the third equation, excuse me. So this was the first equation minus the second, this is the second minus the third. So from the above equations, we can deduce that the vector for the magnetic flux density must be perpendicular to both AX and AY. So the reason for that is this resulting vector has to be perpendicular to both these vectors that we crossed. So that's why it's perpendicular to AX, so it has to be perpendicular to this, and perpendicular to AX, AY, and this. Since these are both the results of cross products in volume B, therefore we can express B in the general form as B is equal to some number C, AX plus AY crossed with AX. So it has to be perpendicular to both of those. And then B also has to be equal to the negative C AZ. So if we took that cross product, that's what we get. So copying that equation over, we can now substitute this general form for the magnetic flux density back into one of the original equations and solve for C as follows. So if we take one of those equations and put this in for B, one of the previous three equations, and we should be able to solve this. So now we have that negative C AX plus AY is equal to B naught AX plus AY. So that pretty easily drops out to mean that C has got to equal to negative B naught, or B is equal to B naught AZ. So now with this knowledge that B is equal to A naught AZ, substituting this back into the original equations now gives us the Lorentz equation equal to that relationship, and again the Lorentz equation equal to this relationship. This part right here and this part right here we can cancel out, and so when we do, we have the expression for the electric field now as E naught in the direction of AX plus AY. So this is the solution to this exercise. Again, we have two fields going on here. We have the static electric field, and then we also have this magnetic field. So the electric field's in the direction of AX, AY, so it's probably at a 45-degree angle, and then the magnetic field is just in the direction of AZ.